In this lecture class, I am going to give you an idea about what is the magnetic field intensity at a specific point near to a current carrying conductor. Here, if you look at the figure, you can see that the blue color is a current carrying element. Current I is flowing through the conductor from bottom to top. There is a small element, a section of conductor is considered. Its length is dl, and the same current I is flowing through the dl, and the dl will produce a magnetic field, and I am going to determine what is that magnitude of that magnetic field at point P, and using that expression we can conclude what would be the magnetic field intensity of a infinite long conductor. Here P is the point, which is the distance r from the small section of the conductor. This is the current element. Its length is very small, very small. And P is a point. The shortest distance between P and the conductor is d. And if you join the two ends of this conductor to the point P, it makes an angle θ1 and θ2 respectively. And similarly, if you make the two ends of the small current element to the point P, the distance from here to P is r. The same distance is from here to here, because the length is dl is very small. And here we can see that angle θ, since these two are same, this θ, the made by the other end of the line with respect to the P, is also same. And here we are taking another a small differential angle dθ. So these are the different parameters that to be brought into the final expression of magnetic field intensity. We know that as per the Biot-Savart's law, the flux density at point P due to the current element, this is the element, the small element, the current element is IDL, is given by, so the magnetic field intensity at point P due to the current element is a differential magnetic field. It is because it is very small. U naught, the current element IDL, and this angle sin theta, which is upon 4 pi r square. And look at this triangle. Here the radius is r and the angle is d theta. Then this arc length is r into d theta. So this arc length is the height of this triangle. There is a small triangle here, you can see that. So the arc length becomes the height of the triangle. So r d theta is the arc length, and the height of the triangle we can use a trigonometric formula to find it out. Let's see that. Now if you look at this triangle, this height equal to r d theta, the triangle here you can see that the hypotenuse of the triangle is the length of the section, that is a dl, and this is the angle. And if you take the sin theta here, sin theta, that is opposite side, that we know that arc length, that is r d theta, just upon the hypotenuse dl. So dl sin theta we can represent as r d theta. dl sin theta is equal to r d theta. So dB become mu naught I, instead of dl sin theta we can write out so r d theta, which is upon 4 pi r square. So there is a common term on both sides, so get cancelled. So now we can write down dB as mu naught I d theta 4 pi r. Now look at this triangle. Here we can see a triangle, and here is an angle theta. This is r, this is a height d, and if you take the sine theta here, so that is opposite side, that is a d by this hypotenuse is r. So r become d by sine theta. So the sine theta is, that opposite side is a d, that is hypotenuse is r, so r become d by sine theta. Substitute it here, so dB become mu naught I d theta by 4 pi. So r is d sine theta, so d goes to denominator side and sine theta goes to the numerator side. Now if you look at this function, we can see that the magnetic flux density is with respect to d theta, and if you integrate the dB, we can find out what would be the magnetic flux density due to the entire length of conductor. So I am integrating here. So when you integrate the dB, it become b, and mu naught I and 4 pi d we can take it out. 4 pi d we can take it out, and sine theta here and d theta here. I'm going to integrate this function, and if you look at the value of theta is changing from theta 1 to pi minus theta 2. Theta 1 to, as the length increases, the value of theta also will changes. So theta 1 to pi minus theta 2. So we can integrate this function from theta 1 to pi minus theta 2. So this become mu naught I by 4 pi d. So integration of sine theta is the cos theta, that is minus cos theta. So upper and lower limits, so theta 1 and pi minus theta 2, and if you substitute this one, it become mu naught pi 4 pi d. It become, if you interchange the upper and lower limit, it become we can cancel this minus, so cos theta 1 minus of cos pi minus theta 2. So this cos pi minus theta 2 is minus cos theta 2, so minus of minus become plus, so this become plus cos theta 2. So this is the magnetic flux density at point P due to the entire conductor. Now let's see that what would be the magnetic flux density if the length of the line extended, if the length become infinity. Oh, by the way, we can also bring out what is the field intensity, because we know that B equal to mu H, and from this expression H is nothing but B by mu, and if you take this mu naught to the left hand side of this expression, we can get the expression of H. So H become I by 4 pi d, so that we can see here 4 pi d cos theta 1 cos theta 2. So this is ampere per meter, so whereas this is a Weber per meter square magnetic flux density. So this we can keep in a box. Now let us move to find what is a magnetic flux density due to infinite long conductor. So if the conductor become infinite long, so what will happen? The theta will, the value of theta 1 will reduce, and when this conductor length become infinitely long, so the theta 1 and theta 2 become very close to 0. They become 0. Then substitute the value of theta 1 and theta 2 here. We can see that cos 0 is 1 and cos 0 is 1. 1 plus 1 is 2. So this become, so B become mu naught I by 4 pi d cos 0 plus cos 0, 1 plus 1, 2. So the B become mu naught I by 2 pi d. Similarly, H intensity, magnetic field intensity is B by mu naught. This is equal to, if you take this mu naught to here, so H, you can find the H is 2 pi d ampere per meter. So finally we obtain the expression of the magnetic field intensity and magnetic flux density of infinite long point at any point around this conductor. Similarly, if the conductor is finite length, then we can also use this expression to find the magnetic field intensity and magnetic flux density at any point on the vicinity of the conductors.